I'm Tim Ventura, and we're joined today by William Munizzi, a postdoctoral scholar at the University of California, Los Angeles. His research surrounds various mathematical aspects of quantum information in high-energy physics, with a primary focus on entanglement, quantum algorithms, quantum sensing, and error correction. William received his PhD in physics from Arizona State University, where his thesis explored the foundations of quantum information and their interpretation in quantum gravity. William is particularly interested in the dynamics of quantum computing resources under the action of operator groups, as well as high-energy applications of various quantum properties. His research has recently expanded to include the optimization of entanglement-based quantum networks and the design of quantum sensing arrays for improved particle detection. William, welcome. It is a pleasure and truly an honor to have you with me today, sir.
Thank you, Tim. I'm very happy to be here.
So I want to jump right into this. This is the kind of story, this is the kind of topic that I get really, really excited about. I want to start with the New York Post story. Google claims quantum chip may prove the existence of parallel universes. And so this story states Google's cutting-edge quantum chip Willow has prompted discussions among scientists about the possibility that we may indeed be living in a multiverse, per a study published in the journal Nature. So starting out, what are your thoughts on this overall?
Yeah, absolutely. So there's a lot to unpack with this particular Google announcement. I think that the two main takeaways are the demonstration of this fault-tolerant surface code at larger scaling, which we can certainly dive into in detail, and then perhaps the benchmarks that they claim for performance standards, and this is where the whole idea of the multiverse comes in. Where are these computations taking place? Because as is stated in the article, they are performing these calculations, which would take not only longer than the age of our universe to compute, but many orders of magnitude longer than the age of our universe to compute.
Yeah, it's really, really exciting stuff. And there are so many big ideas that are wrapped up in something that is practical and working today. That's why I get so excited about it. I've been following quantum computing since around 2000, I think, and it just keeps getting better and better and better. So the Nature article that they're referencing, and I've got links to these in the YouTube show notes, was entitled Quantum Error Correction Below the Surface Code Threshold, and it was very technical. They jumped right into the deep end there. So if anybody references that, they want to be aware of that. This article discusses the fact that Willow can perform calculations that would take a leading supercomputer 10 septillion years, which is longer than the age of the universe. And I think you mentioned that a moment ago. So essentially, a standard computer, I mean, even the best that we can possibly conceive, can't compete with this in terms of performing this calculation, right?
That's correct, yeah. And this just comes down to the fundamental difference in architecture of quantum computers versus classical computers. And so a classical computer relies on this binary architecture where we have these transistors that effectively act as a 0 or 1 value. And by composing these zeros and ones, we can represent objects, whether they be computational objects or they be some sort of mathematical process. And in doing so, we can do everything that first order logic permits, and we can do it faster and faster. But the interesting thing about, and in a sense, the fundamental difference with quantum computing is that now we actually take some fundamental building block of nature to be the object that we're going to compute with. And so whether this be the particular property of an atom, such as like some spin of a proton, or whether this be something like the polarization of light, we allow ourselves the opportunity to use nature itself as the building blocks for computing. And what that does is it relies on this extremely intriguing and non-obvious property of nature, which says that things in nature, the amplitudes, the effective, the weights of of the functions which describe these particular objects, they come in as essentially they square to the probabilities we see in everyday life. And what this allows us to do is represent all of the binary possibilities with just a single one of these qubits, these quantum objects.
Well, so I want to get a little bit into hardware, and I know that that is not your forte. You told me that going into this. You're like, okay, don't get too deep into hardware. I'm like, okay, I'll stay away from that a little bit. But despite the amazing problem-solving capabilities that quantum computers promise, NVIDIA CEO Jensen Huang predicted that quantum computers won't be commercially viable for another 20 years. And this caused quantum stocks to drop 40% for a total market value loss of over $8 billion. So it sounds like, I think partly the Google announcement and partly just quantum computing was causing kind of a bubble to grow. And I think he took the wind out of the sails of that, right? He popped that bubble, at least temporarily.
Yeah.
So my takeaway from that is that quantum hardware is specialized. It's really good at a specific problem. And from what I understand, that problem really has to be set up in advance, right? It's not like just kind of this, hey, let's grab something and throw a computation at it. So it's going to be decades before it's ready for general purpose computing, right?
Yeah, that's correct. And so the idea is that there is, we have quantum computers are designed to do very specific tasks and to do those tasks very well. It's not completely unlike the ideas of large language models, which, as we know, can mimic human speech and interaction, but tend to fail horribly when it comes to performing elementary mathematics. They're designed for a particular purpose. Now, that being said, I don't think that many quantum physicists would claim that we're searching to have quantum iPhones anytime soon. But the idea is that we want to be able to perform the tasks that we know quantum computers are very good at. And that is still a very big question in quantum computing, is determining precisely what are quantum computers good at doing and what can we actually do better or perhaps do just as well as we'd like with a classical computer. And perhaps I can actually leave you with a fun fact. Classical computers can do everything that quantum computers can do, but they would require an exponentially larger amount of time to do so. And so classical computing is indeed extremely powerful. And there's this, perhaps small or at least limited space of problems where quantum computers are expected to demonstrate actual supremacy. And we're really trying to nail that down.
Yeah, and from what I understand, some of the, and again, without getting too deep into hardware, but I've done a few podcasts on quantum computing in the past, and one of the challenges that I understand is that qubits tend to decay quite rapidly. And so with a standard computer, right, once you do your transistor calculations, that transistor maintains a state, and your data just basically stays there indefinitely as long as the power is going. But with quantum computers, you have to basically store that or do something with it very rapidly because it literally just, I believe they would call it decoheres, right? It just goes into kind of a random state. And if I understand right, that happens in less than a second. So
Yes, yeah. So there are, So unpacking a few of the comments you made here, that one of the major issues, practical issues facing quantum computing is noise, what we, colloquially refer to as noise. But this encompasses the whole idea that quantum systems are extremely sensitive. Not only are they sensitive in a very classical sense, that consider, for example, Google's quantum computing architecture. They rely on what are called superconducting qubits. And superconductivity, as I'm sure many in your audience are aware, occurs at very, very low temperatures. Well, anytime that you try to cool a system down to low temperatures, right, you subject yourself to not only the ambient thermal noise of your laboratory, perhaps, but also just any bits of motion at that stage, which could actually be registered as temperature. And this is what is sort of like classical noise. But even beyond this, quantum systems themselves, because of the very nature of quantum mechanics, have a very strange probabilistic reality to them. Essentially, that, as you were saying, given just some amount of time, a quantum system can randomly, if you will, or at least probabilistically decohere into a mixed state, right? And just essentially collapse into a more distributed probability among possible observable arrangements. And this is something we always have to be worried about, along with many other things, when performing calculations using a quantum computer. We can't even trust our measurements half the time. We need to find ways to amplify the correct measurements and essentially suppress what we know to be the incorrect measurements that nature is essentially like screening from the observer.
Ah, okay. Another aspect of this that I have not stayed up on this, but the number of qubits, and that has been increasing and increasing. But from what I understand, it still has to have a few more orders of magnitude before it's very useful. And so, again, last time I looked, it was like, I think they reached 512, and I believe they're up to 1,000 qubits, although I don't want to be, I don't want to commit myself to that. But I've read that that needs to increase several times more before it's really useful for the kind of calculations that might be required for general purpose computing.
That's exactly right. So, with Willow, for example, this Google chip, I believe they're working with 105 superconducting qubits.
Okay.
Um, and then IBM it has also pushed to several hundreds, as you mentioned, and they may even be getting into the thousands. And I'm not quite up to date on that. But the important thing, and the reason why it's necessary to extend several orders of magnitude beyond the number of physical qubits, something which is not necessary in classical computing, is because we need to protect against this set of errors that I had previously mentioned. So
Yeah.
one way that we do that, so if, maybe perhaps to begin with an analogy in classical computing, we also have a lot of the similar classical errors that affect quantum computers that occur in classical computing. We could have various, blips of electrons that move around in ways we don't intend. We could have perhaps some ambient electrostatic in the air or something which affects our devices. But the thing is, we can always rely on what's called redundant encoding. If I wanted to send you a message, I could simply make 3 copies of the message and then send you one, and then you can tell me what you got, and I could say, yes, that's indeed what I have. So you received the correct message. But there's a very important principle in quantum computing, which is called the no cloning theorem, which does not permit us to clone a quantum state or a qubit. And because of this, we can't perform what has become one of the best ways of protecting against error in classical computing. We cannot perform that process with quantum computers. So instead, what we do is we accept that the errors occur, and we implement what's called quantum error correction. And quantum error correction relies on taking a collection of physical qubits. So when you hear these numbers of 105 qubits, that's talking about the physical qubits, the actual superconducting devices themselves. And we say, let's consider a collection of them, perhaps 9 of them, for example, to represent one logical bit. One
Ah,
bit that's going to
okay.
be used for logical processing. And we will perform the operations we want, but then we'll run the whole thing through an error correcting code behind the scenes. And if an error were to have occurred, then we will correct it in real time, and you are guaranteed to get the correct the correct answer from your device. And this is why we need, for every number of logical bits, which already is quite large to perform some of the sophisticated operations we hope to do, we need some even larger number, perhaps even an order of magnitude larger number of physical qubits, all protecting the logical information.
I want to take an aside and ask quickly about like what you would use quantum computing for. This just kind of occurred to me because I think people might be out there going, okay, well, I've heard that it could be useful for cryptography. Other areas, I'm excited about its possibilities for protein folding. I've
Mhm.
heard that the traveling salesman problem just basically goes away, or at least is greatly ameliorated with it.
Mhm.
But what are some of the things that you would use quantum computing for if you had one right now that was general purpose functional?
Yeah, that's a great question. I think I would use it first and foremost. I mean, I consider myself someone who's very interested and passionate about mathematics, so I think I would like to explore some of these these so-called complexity classes that we believe quantum computers might be good at probing. And so you may
Mm.
have heard of things like polynomial time problems or non-deterministic polynomial time problems. But most recently, in the last couple decades, people have been exploring things like these bounded quantum polynomial ideas, right? And so, what can we do with access to perhaps a perfect quantum computer that we can ask it questions here and there, and that gives us some information about solving this. This all plays into what you were mentioning about like the traveling salesman problem. These questions that we know are computationally very difficult. I think I'd like to use the quantum computer to sort of explore some of these abstract mathematical questions and see if we can really nail down these deep ideas of what does it mean for something to be computationally complex in our universe? What does it mean for things to be hard to do? Do quantum computers completely unravel the idea of complexity? We don't think that they do, but it would be interesting to probe these ideas more rigorously.
Yeah. Well, and there are so many interesting, I mean, it opens up a whole new world in terms of computing, and I think it's going to give us new insights into physics too. So I want to get into many worlds a bit here. Let me start out by asking, when we say many worlds, the many worlds interpretation of quantum mechanics, is this parallel dimensions like the TV show Sliders, or is this kind of a mathematical abstraction?
Yeah, so I think that it's important to be precise with the language we use, and oftentimes a lot of people are a little bit fast and loose, and so I'll try to be careful myself. But the idea of dimensions, we have multiple dimensions in our current classical view of reality, right? We can move in three spatial dimensions, and we view time as a sort of pseudo dimension in some sense. And there may be many more. If you ask the string theory community, there may be these compactified dimensions that go all the way up to 22. But the idea is that they themselves are not alternate realities. They are sort of comprise our reality. When we talk about many worlds, we're talking about something that's even more abstract than that. We're talking about something where separate universes exist side by side, each with their own composition of dimensions and histories and causality. And so essentially, it's closer to the mathematical abstraction that you mentioned, but it's considered to be very physical. It's considered to be completely real, the way that you and I are speaking right now in our real universe, just occurring in some other universe. That's the idea.
Well, let me do some screen reading from Wikipedia here. So, some of this I'm literally just going from stuff I found online. But according to Wikipedia, authors including Everett, John Archibald Wheeler, and David Deutsch called many worlds a theory or a meta theory rather than just an interpretation. Everett argued that it was the only completely coherent approach to explaining both the contents of quantum mechanics and the appearance of the world. David Deutsch dismissed the idea that many worlds is an interpretation of QM and said calling it an interpretation is like talking about dinosaurs as an interpretation of fossil records. So my take on that is they are saying, hey, this is real, right? We're talking about, parallel dimensions, like science fiction stuff, which is exciting for me.
Yeah, yeah. The people who subscribe to the many worlds interpretation, if I may be so bold, I know that as you mentioned, David Deutsch and others don't really care for that term, and I certainly don't blame them. But people who subscribe to this many worlds theory, yeah, they believe it is exactly the theory which completely and coherently describes our reality, and that encompasses everything that we know about quantum mechanics, but it also helps tether back to why does quantum mechanics seem so counterintuitive? Some would say it is an obfuscation by the Copenhagen interpretation. Perhaps for your audience, if I may, just a bit of background,
Oh,
right?
yeah.
We when we discuss quantum mechanics in standard textbooks when you're going through undergraduate or graduate school, what you learn is that these the wave function, which is just a general idea for a function which describes a particular quantum system, is essentially the object that you wish to study. But you're not permitted to study the wave function. You don't get to just look upon it. It works, it exists. And in order to interact with it and to make a measurement on a quantum system, you must measure the object. You must measure the particle or whatever it is you're studying. And in doing so, the standard interpretation, the so-called Copenhagen interpretation, is that the wave function then collapses into one of its observable options. And so you've heard of these things called superposition, where you can have a quantum particle like a Schrodinger's cat, perhaps, which exists in some superposed state of alive and dead. But when you observe it, it immediately and instantaneously collapses into only one. And why do we believe that to be so? Well, we walk through our world and we don't see things in superposition. Furthermore, we see probabilities, which are real numbers. And we, as I mentioned earlier, the amplitudes of a wave function are in themselves complex numbers. And so it's only upon observing that we actually see things which make sense with our reality. But this gives a bit of an issue. This is what leads to what's known as the measurement problem in quantum mechanics. The idea that why is it that certain interactions yield measurements and others don't? Why is it that I can observe something like angular momentum, but perhaps I can't just look and observe entanglement? And to essentially get around this issue, Hugh Everett proposed this many worlds interpretation to say that, well, it's not the idea that the wave function itself collapses, but that both of these options, in fact, all possible options, are equally valid. And when me, the observer, attempts to take a look at my system, I become entangled with all the possibilities, and essentially my reality splits. There's a superposed version of me, which is entangled with all the different options. And so I don't need to worry about the counterintuitive nature of having something which exists, we believe, physically exists in a superposition, but then essentially nature screens us from seeing that superposition. Many worlds gives us a workaround for that. That's the idea.
Yeah. Well, and so the many worlds interpretation removes the observer-dependent role in the quantum measurement process by replacing the wave function collapse with the establishment mechanism of quantum decoherence. I took notes, again, I'm right from Wikipedia on that, but as the observer's role lies at the heart of all quantum paradoxes, such as EPR paradox and von Neumann's boundary problem, this provides a clearer and easier approach to their resolution. So one of the reasons that I wrote that down was I have always struggled with this idea of the observer affecting the experiment, right? I mean, like one of the most obvious questions is which observer? And then you get into even deeper issues like Hameroff and Penrose, right? Where if you follow their logic, maybe the universe itself is an observer, but maybe there are different levels of consciousness in different systems. And so it gets really confusing really fast, right? This
Right.
whole idea of the observer changes the experiment, and it goes right into consciousness, which is a very murky area. So
Right.
when I read that, I was like, oh, okay, that's it, quantum decoherence as opposed to observer created wave function collapse. Do you think that there's anything there? I mean,
Yeah, I mean, absolutely. It certainly resolves some of these issues that, you had mentioned, for example, the idea of the EPR paradox. So this was famously, essentially, initial combating of the Copenhagen interpretation by Einstein, Podolsky, and Rosen. But the idea is, it was a bit scary, perhaps, to physicists at the time to consider
yeah,
anything that could be interpreted as superluminal, but we don't see it that way. The idea basically that if I have something in a superposition of, let's say I have a particle in a superposition of spin up and spin down, and I make a measurement, and I have some entangled pair, and I make a measurement on one of the pairs, and I see that it's spin up, I immediately know that the opposing the complement particle is now spin down. And no information could have been transmitted faster than the speed of light to communicate that. And so there was this idea of, okay, well, if the Copenhagen interpretation is to be believed, and the wave function is updating non-locally, and the key word there is non-locally, This is what Einstein referred to as the spooky action at a distance. But it was shown by John Bell that there is no hidden variable idea here, and I think that oftentimes the many worlds interpretation is essentially a attempt to kind of bring locality back into quantum mechanics. I'm not sure that I think that's necessarily an advantageous approach, but I respect that it's certainly it's on some sound footing. The important thing is that when you might do away with certain ideas that are counterintuitive in the Copenhagen interpretation, you must also introduce a complete set of axioms that underlie many worlds. And so this is something people should be cautious when exploring many worlds, is that indeed it resolves issues like the observer being a critical part of the reality, but it also necessitates that there's the addition of these other axioms, which were not necessary in the Copenhagen interpretation, to essentially resolve the rest of physics as we know it to be true.
Ah, okay. So DeWitt has said that Everett, Wheeler, and Graham do not in the end exclude any element of the superposition. Again, this goes back to many worlds interpretation. All the worlds are there, even those in which everything goes wrong and the statistical laws break down. Max Tegmark affirmed that absurd or highly unlikely events are rare but inevitable under many worlds interpretation. And so this was part of something larger. I did want to read that section. So they are affirming that basically all of these possible virtual worlds or parallel dimensions do exist, including highly unlikely ones, even ones where fundamental laws of physics break down. And so, again, going back to our sliders analogy, that means, from what they're saying, we have parallel universes where the Nazis won World War II. We may have one where Superman exists, right? So classic science fiction tropes, that opens the door for classic
Absolutely.
sci-fi right there.
Absolutely. Yeah. And there's also, I think, one of the most fascinating consequences that some of your audience may have heard of before is this notion of quantum immortality, right? So if there's a probability that I were to drop dead at any given moment, well, then there must exist the probability that I didn't. And so what happens in the chain of universes that I just kept getting lucky ad infinitum, right? And so did I just become immortal in some universe? I don't know. This is some of the weird consequences that come out of this many worlds idea.
Yeah, and so again, going back to quantum computing, if I understand correctly, the idea is that it, instead of performing a series of computations like a standard computer, basically each of these qubits performs one computation across an infinite number of parallel dimensions, and then somehow it self-resolves to the correct calculation, presumably across all of them, right?
Right. Yeah. And I think that's the general idea, as we had spoken about earlier. Where is this computation taking place? Which I think is a valid question to ask. I'm not sure how convinced I am of the many worlds resolution to this, but I think it is fascinating and certainly a very scientific question to ask. That if we are dealing with things which we know would take orders of magnitude beyond the age of our universe to realistically compute, then perhaps you can say, is this being farmed out to some superposition over many different realities and somehow resolving in what we observe in our current universe? It is important to again be cautious when thinking about, we don't expect these universes at all to communicate with each other. We do genuinely believe that they separate, and perhaps they are there could be some notion of entanglement that spans across them, but nothing where we're going to be communicating between observers from one universe to the other. So I don't think that I just want to caution anyone from believing that the computation takes place in some universe and then is sent via a communication to this universe, because that is certainly not what's proposed by many worlds.
Yeah, yeah. Again, from what I've read, and I may not be expressing this correctly, but the idea was that it takes place in all of them simultaneously, and then as some kind of a wave function, basically collapses back down to the correct answer. So one thing I wanted to ask was, if quantum computing proves, put my fingers up there, if it proves the existence of multiple dimensions, does that fundamentally change physics, right? Because many worlds is an interpretation, and from what I've read, in fact, when I was doing story research for this, I got yelled at by a couple of physicists. They're like, that's not real, right, Tim? And I was like, you know what? This is exciting stuff. So, if we're able to prove the existence of these multiple dimensions, how could that potentially change physics?
Yeah. Well, I guess I'll begin as an optimist and say I think that it would certainly change the way we view physics. And ultimately, for physicists, that's a very important thing. Whether we like to admit it or not, we consider ourselves like the great objective operators of the universe, but the reality is that we do care very much about the interpretation of these results, and they ultimately underlie what fascinates us about physics in the first place. But then to play the curmudgeon, I would say it wouldn't change much for me personally. It wouldn't change much for many physicists because I'm ultimately bound to this universe and the experiences that I have in this universe and the physics I observe in this universe. And that's completely independent of the interpretation of quantum mechanics as a sort of philosophy of what goes beyond what we can use quantum mechanics for and what we observe about quantum mechanics in this universe. And so your mileage may vary depending on the individual. I think that some people would be absolutely stoked, and kudos to them for that. I personally would just probably say, "Wow, that's very cool. That's amazing," and then I would carry on with my day-to-day physics.
Yeah, well, that's a good point. And what you said about being bound to this universe is also interesting. And that goes to my next question, because if quantum computers operate by interacting in some way across multiple dimensions or many worlds, does that give us a tool to potentially influence those other dimensions for like communications, time travel, dimension travel, right? Like you can go into the TV show Sliders, or maybe viewing the past or the future. Do you think that those might be possibilities?
Yeah, so, well, we're always viewing the past in some way, right? Because in our universe, light takes finite time to reach the observer. And so, as you know, you look at the sun, you're looking at the sun from 8.5 minutes ago. But I bring that up not to be difficult, but the idea of time travel in our universe, it exists as these, what we call closed time-like curves.
Yeah.
So this is just a statement of GR, essentially the idea that we have things which move in time, we call time-like motion. We have things that move in space, called space-like motion, and we have most things, or all things, which do both. And what we try to avoid in GR is these closed time-like curves, the idea that I can propagate forward in time and then somehow loop back on myself and close that curve to where I've essentially reached my own past, right? And that's the idea of time travel. I don't think that the many worlds interpretation gives anything more or less to those ideas. I think those ideas are essentially bounded within each universe. And so if causality is to be believed, and of course we think that to be the case, but if causality and general relativity are correct in our universe, I think they would be correct in other subsequent universes obeying our physics. The idea of influence is a very interesting question, though. The idea of, are these universes somehow entangled with each other? Whereas we might not be able to use that entanglement for communication, but could we perhaps make use of that, or do they influence each other? Maybe that's the phrase. Do they influence each other in some way that we're unaware of? I have no idea. I think that it's certainly possible. I think it would agree with the foundations of many worlds. Influence in the sense that if I were to get up and open my door, that there's a universe then that it must exist where I don't. So in that way, that's a sort of influence, but nothing that I think would lead to any interesting sci-fi possibilities like time travel, unfortunately.
Yeah. Well, and when I started to think about that, I was like, the possibilities are so endless, right? That we quite literally can't imagine what we could use this for, in the current time. But it does open this really remarkable door, at least potentially, And so it's one of those things that leaves the mind spinning. Now, in
Absolutely.
terms of time travel, my thought was that this might be able to solve the grandfather paradox, and that's the good old trope where basically if you travel back in time to kill your grandfather, you wouldn't be born to travel back in time, hence the paradox. And some people have speculated that if there are parallel dimensions or multiple timelines, that instead of creating this closed time like curve that brings you back to where you were, you're actually just traveling to a different timeline. So there's no paradox. So,
Hmm. Yeah, and I believe that in the end there would ultimately be no paradox. I mean, general uh, essentially a sort of academic trope that's touted about is the idea that if you have a paradox, it's essentially just a shortcoming of your understanding or your theory. We don't believe that paradoxes themselves are necessarily to be believed. It's essentially just revealing to you, hey, something's wrong here, and there's a small modification perhaps needed in your understanding to resolve it. And so I think that I don't think many worlds would essentially give us any way to perhaps explore the grandfather paradox, fascinating as it is, but perhaps would give some resolution in an abstract way that essentially resolving the idea that these two things can simultaneously occur, just not in ways that can communicate with one another.
yeah, yeah, it's absolutely amazing. This is one of those ideas that inspires the imagination, right? And that's why I'm
Hmm.
so excited to have been able to go over this with you. So, William, let me thank you so much for your time today. It has truly been a pleasure and an honor having you with me. Let me close by asking what is coming up for you as we go into the first few months of 2025, and what do you anticipate seeing in the near future in quantum computing?
Yeah. As you said, I'm a postdoc. I'm just working on papers all the time. Which I enjoy. Um, I'm particularly interested in a lot of the foundational questions of quantum computing and quantum information. So I'm really interested in recent updates regarding entanglement, the role of quantum computing in applications to quantum gravity, this idea of quantum magic, which perhaps we'll have to discuss that sometime. This is a whole nother subject.
Mhm.
But all of these things, which are big advances that are occurring by the day in the field, we're finding out so much about nature, and I'm excited to be a part of it. A lot of great conferences coming up. As you've probably heard, the UNESCO declared this the International Year of Quantum. And so this is a very exciting time to be in this field, and I encourage all of your listeners who might be interested to keep looking into opportunities in quantum. It's definitely going to be a revolution for our reality. Yeah.
Amazing. Thank you again so
Yeah.
much for your time today, sir.
Yeah. Thank you, Tim. I really appreciate it.